Hello and welcome to this video about the classifications of matter and just some basic introductory vocabulary that we'll be using in the class. Okay, so we're going to talk about matter in this course. That's really what the study of chemistry is. We study matter and how it changes. So matter is just anything that has mass and takes up space. And the key idea for chemistry is that matter is composed of particles. Okay, so pure substances are materials, types of matter that are made up of only one type of particle. So in pure substances, we have both elements and compounds. Elements are the simplest form of matter, and what makes something an element is that it's made of only one kind of atom. Okay, so here's the periodic table, or a periodic table, listing all the elements, some of which occur naturally, some of which have been made in labs, but now there are 118 recognized elements, about 90 of which occur naturally. And so those are the different types of atoms. So there's only 118 types of atoms, building blocks. So it's like, imagine building with Lego, and there's only 118 different shaped pieces from which you then build everything. So elements are made of one type of atom. So you can have molecules with elements, you can have single atoms for elements, big networks of atoms for elements, but there's only one kind of atom in an element. The compounds, on the other hand, you always have at least two different elements combined. You can see in this little picture, there are small gray circles and there are small red circles, and they seem to be connected to each other. So with compounds, you always have two or more elements combined, bonded. Okay, and so I'll get to that more, but that's the distinction. So one type of atom versus more than one type of atom for our pure substances. Now, just to point it out here, not really so essential right now, we'll come back to this, but to let you know that actually there are things called allotropes. It's a little confusing, but an allotrope means a different form of an element. And so some elements actually exist in multiple different forms. So oxygen, for example, there are two main ways that you find oxygen by itself in our planet or just in the universe. And the main one is oxygen, O2, the stuff that we breathe. But actually there's another form of oxygen called ozone. Now they're both elements because they're both made of one type of atom, just oxygen atoms. But the oxygen actually can bond into two different types of molecules, and that gives it different properties. Ozone, if it's around at normal ground level and you breathe it in, it's actually bad for you. It's toxic to you. It can irritate your respiratory tract. Whereas oxygen, obviously, is what we breathe in to stay alive. So they have very different properties just in that subtle little difference. So those are two different forms of the element oxygen. And then there's lots of different allotropes of carbon, graphite, which is in your pencil, diamonds, and then there are additional forms as well, like graphene and buckyballs and this and that. So some elements are going to have different forms of the same element. Not a big deal at the moment. I just wanted to put it out there to keep in mind for later. Okay, compounds. We're combining things chemically, combining elements chemically. So you start with hydrogen, an explosive gas, and oxygen, a gas that you need to burn to support combustion. And when you combine them chemically, you make water, which is the stuff that puts out fire. So one of the most amazing things about compounds is that the elements that you combine, you really do create a totally new and unique substance that doesn't necessarily have any of the same properties as the elements that created it. I always find that to be amazing. So this is, we've got hydrogen here, that's an element. We've got oxygen, O2 is how it normally exists. And when it reacts, it forms H2O. And so when we look at the formulas, we can see that hydrogen just has one chemical symbol, so it's an element. And the little 2 tells me it's in a little molecule with two hydrogen atoms. This is an O2 molecule, also an element since there's only the symbol for oxygen, O. And then water is a molecule that has two hydrogen atoms and one oxygen atom. If there's nothing written, it's assumed to be a 1. So this is a molecular formula of water. It shows us that one molecule has two hydrogen atoms and one oxygen atom. okay? But water is a compound because I can see two different element symbols. Okay, another example, sodium is a very reactive metal. It will catch fire if you touch it to water. Chlorine is a poisonous gas, and yet when you combine them, you get sodium chloride, table salt, which makes food taste better. So again, another example of a compound, and symbol-wise, I see Na for sodium, I would see Cl2 for chlorine, and when I combine them, I get NaCl. So distinguishing between elements and compounds is looking for one element chemical symbol, like Na, versus two symbols together, two or more symbols together, like NaCl. Na, I don't see a little number after it, so I would interpret that to mean sodium atoms, single atoms, because there's no small number. But because there's a 2 here, then I would interpret chlorine to mean chlorine molecules. So the particles of chlorine must be molecules because of that little number. Okay, another minor detail to keep in mind, just so you keep your mind open, like with the allotropes thing, I'm never going to ask you to define the law of multiple proportions, but just to keep in mind, elements can often combine in more than one ratio. So H2O is water, but hydrogen and oxygen form a different compound, H2O2, which is called hydrogen peroxide. They are very different, and so the different ratio makes it a different compound with different properties. Carbon, hydrogen, and oxygen have got millions of ways that they can combine together. So just keep your mind open. Just because you're used to seeing H2O doesn't mean that's the only ratio that hydrogen and oxygen can combine in. Particles, atoms. Atoms are single particles of elements. Molecules have to have, now it says particles composed of one or more atoms. That's wrong, sorry about that. Should say 2 or more atoms, obviously. If you just have one atom, it's an atom. So molecules have to have at least 2 atoms bonded together. So it's a bigger particle, or generally speaking, it's a bigger particle. It's made of multiple atoms, and now it's a distinct little particle. So we've seen that you can have elements that are made of molecules and elements that are made of atoms. And then you can have compounds that are made of molecules as well. Now, the third sort of component particle that we're going to see a lot are ions. Ions can be single particles, so they can be monatomic, or they can be polyatomic. So you can look up here. This right here represents a magnesium ion, and ions have charge. So atoms can gain and lose electrons. And so this is a magnesium ion. It has lost 2 of its negatively charged electrons, and therefore it's ended up with a 2+ charge. Whereas this thing over here, this is something called a hydroxide ion. Not anything that you need to know just yet, but I can see it's made actually of O bonded to H, kind of like a molecule, but it has an overall charge of -1. So this is a hydroxide ion. So we've got single atoms, and we've got single ions, and then we've got molecules, which are atoms bonded together, and then we've got polyatomic ions, which are atoms bonded together, but there's an overall charge. We have fun words for positive and negative ions. Cations are another word for positive ions that you'll hear me using. You can remember that with the word cat has that T that looks just like a positive sign. So cat ions, not cations, cat ions, and then anions. You can think of onions. Maybe you have a negative connotation with onions because they're stinky. They kind of sound like that. Or you can remember a negative ion. Or if you just remember that cat is positive, then anions must be negative. So just some vocab that we're going to be using along the way. These are the 7 polyatomic ions that you will be expected to know one day on your IB exam. So I'm just going to throw them out there now, and I'll put them up on the wall, and we're going to start learning their names and their formulas and their charges. But I'm going to skip past that for now. Mixtures are not pure substances because mixtures can have different compositions. So salt water, sugar water, even things like metallic alloys, brass. Not all brass is the same. You can make different qualities of brass that have different amounts of each of the component metals. You can make different types of salt water that have different levels of salt in them, different concentrations of salt. So that's what it means to be a mixture. The things that have been mixed are just physically mixed together. They're next to each other, but they haven't actually reacted and made anything new. We've got heterogeneous mixtures, which have a non-uniform composition. And we've got homogeneous or homogeneous mixtures where we do have a uniform composition throughout, down at the particle level. So everything is mixed nice and evenly. We mostly deal with homogeneous mixtures in the form of solutions, so things that have been mixed into water, so they are aqueous solutions. And we say we mix a solute into a solvent, and that's how we get a solution. More on those later. Finally, chemical symbols. We've seen some of this, but when you're writing chemical symbols, it's very important to pay attention to capital letters versus non-capital letters. Just to point out a distinction with the letters C and O. If you write it this way, it means the element cobalt, and if you write it this way, it means carbon monoxide, which is a poisonous gas, right? So if it's just an element, then the first letter is capital, and if there's a second letter, it's lowercase. Whereas if I see these two capital letters one after the other, I think carbon, and then I think oxygen. So pay attention to those uppercase, lowercase letters. If there's more than one thing together, then we're going to use little subscripts like this. So N2, H2O, that means we're dealing with molecules. And those little numbers are telling us how many of each element is in the compound. If there's no number, like here, that means it's a 1. Superscripts are what we're going to do for charges. So like when we saw that magnesium ion, Mg, the charge gets written like that. If it's just a single charge, we usually leave the number out. If it has more than a single charge, like a 2 or a 3, the number comes before the charge symbol, which is a little weird, but that's the convention. Sometimes you'll see coefficients in front of numbers, especially when we balance chemical equations at some point. So like there's an example, well, I'll just do the example down below since I've already done that. So if we look here, this versus this means two different things. The 2O means 2 atoms of oxygen, whereas the thing on the right represents 1 molecule of O2, right? So if the number is little, if it's a subscript, that implies something about bonding, that things are bonded together. If something is in front, it's just telling you about how many of that thing there are. Okay, so again, 8 atoms of sulfur versus 1 molecule that has 8 sulfur atoms in it, all bonded together. H2 plus O2, so this is like a mixture. You got H2 hydrogen molecules and oxygen molecules next to each other. When I write them like this, it implies that they're bonded together. So now I have a compound. And then these guys at the end, these are ions. So this is a 3 plus ion, a 1 minus ion, and these are polyatomic ions. So these are many atoms bonded together and they have charges. We're also going to see some symbols that get used to tell us about the state of matter, solid, liquid, gas, and aqueous, which means dissolved in water. And that is sort of our foundation vocab and some foundation conventions with symbols and numbers that we're going to use throughout the course.